goes and introduce most of the presentation.
Thank you. Hello everyone. So I'm Pedro, I'm a postdoc at the University of Oxford. This is joint work with a student from Utrecht University. So it's about generating harmony and accompanying melody for the generated harmony. I should perhaps start by toning down your expectations a little bit. So you've seen this nice live coding demo on the video that I was showing you at the beginning. So it's perhaps good that beautiful was removed from the call for paper, because maybe then the paper wouldn't be acceptable anymore. It's very preliminary and exploratory in nature. I didn't really intend it to generate perfect music, also because I don't think I could do that in a few months or anything. I think if you want a real automatic composition system, then this is going to take lots of people, lots of effort for quite some time. So I just wanted to explore what you could do, in this setting, and to see what we could achieve in a simple and easy to extend way. So this is all based on a model of harmony that I first talked about. So I developed it together with another colleague from Utrecht, Lars de Haas, and I first talked about it at ICFP 2011, as an experience before. And there we focused mostly on the potential for showing harmonic structure as a tree, so that you can see the relationships from the chords in a song in a tree aspect, so that you can visualize the hierarchy present in the harmony. Then, using this model, we also developed a system for finding cover songs based on harmonic similarity. So if you have a song that's a cover of another one, they might change the melody, the instrumentation, the rhythm, speed, etc. But the harmony often, or almost always, stays nearly unchanged. So if you want to find cover songs, looking for harmonic similarity is a good thing. We talked about this at ISMIR 2011. And then at ISMIR 2012, we talked about how to improve audio chord recognition. So if you just have a WAV file or an MP3 and you want to find out the chords, you do a lot of signal processing, and at some point you're left with basically, for every beat, a list of candidate chords that could fit that beat, and which each of them has an associated consonant. So then we use our model of harmony to find out which chord is more likely to be present at that stage, given what's been present in the past. Out of this also came a company, Chordify.net, which does exactly that. You give it a YouTube song or an MP3 and it tells you the chords. Very successful. We have over 100,000 visits a day, so that went quite well. Also using all Haskell with our model in the backend. Then last year at Farm we talked about a system for automatic harmonization. So there you are given a melody, and the task is to find just the chords for that melody. Again, using the model, we try to find good sequences that match the melody and at the same time still make sense among themselves. And now this year, I'm going to tell you about what I named FCOM, where you don't start from anything, you start from scratch. You first generate harmony, and from that harmony you then try to come up with a melody that fits the generated harmony. So, this is from what we've shown, well actually, this is similar to what was shown at the ICFP 2011, our first work. And there, you see the chords at the leaves. C major, E minor, F major, etc. And that is your input. And from these input, just the chords, we derive the tree structure. And that says, well, there's a tonic here, and we're in C major, so that's the first degree, and then there's a dominant structure with a subdominant and a dominant. Subdominant is expanded into a third and fourth degree, and the dominant has a secondary dominant of the second degree, then the fifth degree, which finally falls back into the tonic. So your input was the green stuff together with the key, and then we derive this structure, and you can see what's going on behind these chords. But you can also see this tree the other way around. It could be that I just started looking at my model and saying, well, I can come up with a piece, and the piece has a phrase. A phrase could perhaps be in this form, tonic, dominant, tonic. And so then by figuring out these things, or by randomly generating them, you determine what the chords have to be. So that's what we do here. We have the structure and we just randomly generate it, not fully randomly. We generate them and then the chords just fall out naturally of the structure. So the first thing you have to do to use our system is to define the model, define the rules of harmony that you're interested in modeling as the first step at the end. Then I say it's not fully random because you don't want each rule to have the same weight or each sequence to show up in the same probability. So we allow you to set weights on the rules that you defined in the first place, so that you can bias the generation to go towards to prefer some rules over others. After that step, you're done with the harmony, so you're going to get a sequence of chords, and you're left with the task of generating a melody that goes along with that sequence of chords. And there we have 4 steps, but I'm going to talk about them later on individually. And at the end, you have a melody together with harmony. What you should note also is that there is no rhythm here. I did not look yet at the problem of rhythm. I think that's, again, another very large problem on its own, and a very interesting future work, but there's not yet that rhythm. Okay, so into our model of harmony. It's all implemented in Haskell as a large data type, but we prefer, or actually we like showing it as a kind of a parameterized context-free grammar, because then you don't really need to know any Haskell for understanding it. And also, if you do know Haskell, then you will see very easily how this is translated to a data type. So, we use a variable here, m, because there's 2 modes, major and minor, and some rules only make sense for major modes, some rules only make sense for minor, and others make sense for both. So, if we have the m as the variable, it means it makes sense for both. So, a piece, independently of it being in major or minor mode, is a sequence of phrases. What are phrases? Well, we just say they're either in the 1-5-1 form, tonic, dominant, tonic, or they open with the dominant and end with the dominant. We could, for instance, have also a 1-5 model that ends with the dominant. Just for this example. Okay, now the tonic. Very simple, or perhaps the simplest tonic you can have. In the major mode, the tonic extends to the first degree of the scale, major. Actually, the superscript here indicates that the chord itself is major, minor, dominant, or diminished. But it's major, we don't show anything. But the chord has to be 1M. So the typical musical convention would be to use a underscore, lowercase I here. But we just do this because it's more convenient for naming of constructor anyway.
So the min says that the piece is in.
Yeah, the lower min is for the piece.
And the m is for
the upper m is for that chord itself. Yeah. And there's an implicit uppercase m there for all the ones you don't see. Dominants are a bit more complicated. So we have 3 immediate expansions to chords. It could either be a 5th on a dominant, major, or a 7th diminished. Or we can further subdivide it into a subdominant first, so preparation of subdominant, and then again a dominant, or a secondary dominant which goes to the 2nd degree in dominant and then the 5th degree in dominant. What are subdominants? Well, in the minor mode, that's only the 4th degree in minor. In the major mode, we make a few more expansions so that to allow us also to have the 3rd degree there, or the 2nd degree. Finally, at the end, once you pick the key, for example, in this example C major, you can translate the relative scale degrees into actual chords. So the first then becomes the C major, the first minor is the C minor, etc., etc. So you have to give this a roll combination. So, rather simple, and you can argue whether some of these should be here or you might want to put many others. But the thing also is that it's very easy to change them, and you can adapt it to your own liking, as we're going to see soon. So, how do we do this in Haskell? It's just using GADTs, or actually just data types, and we use the GADTs for the variables that we have. So, we said that a piece was a list of phrases, and that's still the case, only that we parameterize the phrase over this mode which can be in major or minor mode. We hide this in an existential, but that's a detail. You might notice also that I'm using data type promotion here, so the mode is actually a data type with two constructors, and I use it here as a kind with two types in it. This is just because I need this both at the type level and at the constructor level and at the type level, so data type promotion is just useful to avoid duplication of these things. Now the phrase, remember, could be 151 or 51, so that's a phrase 151 in tonic, dominant, tonic, or a phrase 51 in dominant, tonic. Those are two ways of building phrases, and it's independent of it being major or minor. Tonic, it could either be a scale degree, the first scale degree in major, and that builds a tonic in the major mode, or for the tonic in the minor mode, you build a scale degree 1 with minor quality. The same for the dominant. We have these 5 rules in the grammar, then we have these 5 constructors in the data type. All of them are not fit to the mode. So you see here that the translation from this parameterized grammar to Haskell data types is very standard. At the end, at the least, we have the scale degrees, and here's perhaps worth saying a little bit more. So we have 7 diatonic degrees from 1 to 7. We have 4 possible qualities for each chord. Again, a bit arbitrary, but just that's all I think for now. Major, minor, dominant, and diminished. And the scale degree has then a diatonic degree and a quality. And, well, yeah, a single constructor that just stores the actual chord that you're in. So now, we have a model, we have a data type that encodes harmony sequences. So how can we generate these sequences of chords? How can we come up with new music, new chord sequences? Well, that's easy, right? We just use quick check. We know that's how you generate random test data in Haskell, so why not apply it to sequences of chords? So we just give arbitrary instances for each of the data types in our model. But I don't want to do this by hand. So I've shown you like 5 or 6 data types. That's not a lot. You could do it by hand, but previously we worked with models that had, I don't know, 40 constructors in total or so, divided over 20 data types. And you really don't want to give these arbitrary instances by hand, also because these are GDTs, so the instances become a little bit more complicated. And once you're playing with your model, you want to add new rules, you want to remove rules. You really don't want to have to change lots of code every time you're just playing with the model. So we use generic programming that allows us to get functions that work on any data type. And you can change the data types and the functions still work. So completely what I'm using is, well, just looks like this. Basically, you get a function gen that gives you a quick check generator of alphas for any alpha, as long as that alpha is representable. And I have some template Haskell code that automatically gives representable instances for all my GDTs in the model. So then I can change the model as much as I want, and my generator still works unchanged. It will still generate random sequences of data. Now, I don't exactly want just purely random. I want to be able to say something about which constructors should show up more often than others. Because, well, from a musical perspective, these rules are not always used with the same likelihood. Some of them appear very often, others are rather random, others are rather infrequent. So the way to combine, so this is a bit of a tricky issue because you want to say, you want to give ad hoc behavior to a generator that's supposed to be generic. It's supposed to work for all data types. So the way I worked around it is by having this generator take a parameter that says, for this constructor, give it this weight. So you can say for every constructor in your model, give it higher or lower weight. And there's a default weight of 1, so you don't have to list all the constructors anyway. You can also just pass an empty list and that will still work. But if you want to change the weights, you can just change them. And this then is another way that you can change your model and the generators will still work. And you can still give some form of ad hoc behavior for your generators so as to bias the generation of chords. Now, how do you actually use this? So here's an example. From the model I showed you before, you remember there were 2 another 5 DOM constructors, and now I want to say that the 4th and the 5th should show up more often, so I give away the 3 to this one, away the 4 to this one, and then basically this is the important part, which is sample the generator. That's just going to generate 10 random values, and then the rest is just printing it on the key of C major. And then you get sequence report. So this is one example run, and you'll find out that one of these is probably corresponding to the tree I was showing. You can also display these chords on a musical score, and then you get this. There's no attempt at doing any sort of pitch spelling here or voice leading, so this is just plainly showing the chords as they were generated. So, okay, we can generate chords that make sense in a harmonic, according to harmony theory. That's the first step. Now, we need to come up with a melody that goes together with the harmony. And that's perhaps where the hard part of the work begins, because melodies are perhaps less structurally determined as opposed to chords. And there's a certain interdependency. When you're composing, you're typically not first coming up with a harmony and then finding a melody that goes along. This is, you do both at the same time. So. But for this task, we were given the harmony, and now we're just going to melody. A very simple idea that I come up with is to, okay, for every chord in the input sequence, you just generate first a list of candidate melody chords. Which melody notes could be present for that chord. And I just say, well, that's going to be all the notes of that chord. So, for example, here I'm going to say, oh, the possible melody notes here are C, E, and G, the 3 notes of the chord. Then we immediately filter out some choices that are not so good, like you should never end a piece on anything other than the 1st or the 5th degree of the scale, so we filter out those. And you should probably also only begin in the 1, 3, or 5 of the scale, so some trivial filtering there. Then we go through the whole sequence and we decide to focus on one specific note, and that's going to be the target note for that chord. After that, we have a sequence of notes that are kind of disconnected for each chord, and now we have to connect them, so I call that embellishing. You go through each of those candidate chords and try to connect them in some way. The nice thing about this is that, well, we're in a functional language, and this is just composition. We have 4 steps, so we generate the candidates, we refine them, we then pick one per chord, and we embellish the melody, and we're done. We have a song. It's all monadic composition because during this process you want to keep a lot of state around, like the chords that are present before and after, what melody notes have you already picked, etc. I'm not going into a lot of detail here, also due to lack of time, but you can find the detailed description in the paper. So now I guess it's time for some examples for me to show you the beautiful melodies and harmonies that my work generates. So here you can see the harmony tree. So we first generated these chords, which are graphed here, and then this is the melody that was generated. I'm going to play it in a second, but stressing again what you should not expect. You shouldn't expect any form of voice leading here. If you want to actually transform this into music, you obviously have to find a way to connect these chords into, well, the proper voice leading, which we are not doing here, but it's a separate problem and can be handled separately. And also you might notice that my notation tries to do away with as much rhythm as you could imagine. So I'm not saying that there are 4 notes here and each of them has the same rhythm or anything. There's just no rhythm. The rhythm is the process that will have to come later. But for playing them, I will just divide them equally over the time. So these 4 are going to take 1 beat, and if there's 3, they're going to be each of them will take a third of a beat, etc. So let's listen to this. Thank you. It's not amazing, but it sounds alright, right? I mean, embellishing process is a bit too continuous at the moment. It really tries very hard to continuate things. It does it by producing scales, but there's a little discontinuity here. That's basically because this note and this note are the same. So you can't do scales to connect them, but then it does something different. So that's actually the most interesting one. Second one. Really like scales. But the thing is, even with scales, this is already not trivial. In major mode, it's still okay, but in minor mode, scales are already not trivial because an ascending scale and a descending scale are not equal. You have to take care of the melody. For those of you who know music, you might imagine the problems you run into. But still, I found it in a way surprising that you already run into quite some issues, even with such a simple algorithm. Here's an example in minor mode, though. Carefully chosen. So this, I think, sounds pretty okay, and it doesn't do any obvious mistakes. The resolution here, for example, second to first, it's fine. Sometimes it does things like having the seventh of a chord and resolving it upwards instead of downwards, because I didn't put any knowledge into the system that it has to resolve seventh downwards and things like that. Anyway, conclusion. I try to make it simple, easy to understand. So I hope, even if you have no real knowledge of Haskell, but you have knowledge of harmony theory, you can understand the model in terms of these grammar rules that I've shown you, and then see how easily they map to code, to Haskell. And you could potentially then just write your own rules easily by seeing how the other ones were written, and you can adapt them. Also, the melody generation tries to stay as simple as possible, just a composition of steps, each of them which can be easily changed or adapted. My hope is also that this can be a way for getting students into this kind of work, and that they can then focus on one specific part of the pipeline or something like that. But yeah, lots of room for improvement, of course. Composition is hard. It's not by chance. It takes quite some years for people to learn how to compose decently. So no voice leading or counterpoint whatsoever, although I think this is a separate problem in a way and can be handled as you could just make it another step after the generation of melody and harmony to do the voice leading and counterpoint. Repetition is not handled by itself. It arises naturally, but that's not really how it goes in music, and certainly in melody. Repetition is a key aspect of melody. You can't just hope for it to happen. You have to make sure that it will happen. That's what gives melodies a recognizable element. So I think it would be good to incorporate repetition in some way to this model. The embellishment, well, you've seen it. It's at the moment very primitive, just the scales up and down and some less obvious things as a repetition of the notes, but you have plenty of possibilities there. And all the rest. Nothing was done about rhythm, nothing was done about form, instrumentation, or dynamics, just to name a few of the aspects of music that are still to be covered. Anyway, thank you for your attention.
So, questions? I'm a little weak on harmony theory, so I don't know if this question makes sense, but in the musical theory, is it possible that when you have a sequence of chords, you have a rule that constrains the relationship of, say, this sequence of chords, and then another one which constrains an overlapping sequence? Your rules are tree structured, so that your system can't handle that. Is it possible in the musical theory, and if so, how would you extend your system?
I would argue not, but I'm sure that certain musicologists would argue yes. I have a rather Schenkerian view on this. I mean, I really believe that harmony can be explained hierarchically, and you shouldn't have these kind of overlapping structures. But yeah, I'm sure in a different setting, some people might be very offended by this statement. I certainly think that is not a limitation of concern to this work. You can do perfectly good and complex sequences just by plain hierarchy. I'm much more worried about rhythm and most of those things that have not been added.
Wouldn't you run into exactly this problem when you want to introduce rhythm?
Oh yeah, I mean, so that's I think rhythm cannot be modeled in this hierarchy. Right? I think this works great for harmony, but rhythm, the structure there is different. But I don't know how you combine these two. I don't think that because I'm using this hierarchy for the harmony, that will force you in the rhythm to use the same. Especially because if you first generate the harmony and then the rhythm, you're free to generate the rhythm however you want.
How much code is that?
Maybe I can show you. It's not a lot.
We try to make it very so the model itself
So the model itself is, it's common. I basically removed lots of stuff that I had from my previous model. So we had chains of secondary dominance, tritone substitutions, all of that. I removed all of that to have a very simple model. 50 lines of code for the model. And then the harmony generation is mostly here. And that's, well, this is the first step. Generate all possible chords, all possible candidate notes for a chord. Then this is the filtering step, 10 to 20 lines. Then picking one note per chord, again 15 lines or so. Then embellishing, a little bit longer, I think 30 lines or so. That's the chord. So, of course, there's some more stuff around it, but I'd say very little.
In terms of putting knowledge into the system for filtering and then setting weights and such, have you tried or looked into extracting them automatically from recorded file data? Like, I don't know, with style limitation in mind, write music like this setup?
Right. No, that's the short answer. And also, I've never looked into these learning-based approaches to music. I've always looked into knowledge-based. So I devise the model, or someone with some music and knowledge comes up with a model. Because the way I do things, to be able to learn would mean that you have to come up with a data type from, after seeing, 1,000 or 2,000 sequences of chords, you come up with a data type that explains the high-level structure. I really don't know how to do that. That's like coming up with a grammar after seeing lots of sentences in the alphabet. It's a really hard problem. So I think if you want to do that, you should really just do Markov chains. I think this kind of work is not suitable for that. I do see the potential for learning from data and importing by essential, but just not that.
How strong is your proposals? There are plenty of work that has been done around automatic chord generation, melody, etc.
Yeah.
And how easy it will be to incorporate this job, this work, this proposal, this approach into your system?
You mean to incorporate the other work?
The other approach, the other methods, the other heuristic.
Yeah, so I think lots of the work that has been done is based on learning techniques, so that either...
On grammar as well.
That, but well, we are based along that. So, our work follows along that line. And also Dave Templeby's work, Martin Rollmeyer, so people who have been modeling the structure of music as a grammar, we follow along that line. And our main concern is just that some of those rules are not really implementable because they're highly ambiguous. So if you just add a rule that says I can modulate to any key at any moment, then that implementation is really tricky because you say, every chord is just a modulation. So there are some constraints when you start implementing it. a lot of it we can export through.
So I'm just going to invoke Chair's privilege and ask one final question before we move on to the next talk, and that's clearly made a lot of use of very recent Haskell type extensions, and in the spirit of the whole ICPF conference. And the question which Eisenberg that asked late yesterday is there anything in the direction that the type work is going that actually it could present some opportunity or a limitation for you?
Opportunity, don't we? I mean, I eagerly use these things. I might even have been partially to blame for some of them to be in the language. But it also helped me in, it is not just an application, it also forces me to revisit my own generic programming libraries and to make them able to work with this more expressive type system that we have. So I think the synergy is really good. It forces us to move forward on multiple aspects, not just the musical modeling, but also the plain functional programming support.
So Parkwood Publishing today would be writing the well-typed clavier. Parkwood Publishing today would have the well-typed clavier.
Yes.
Okay, so let's thank Pedro once again.